for this program is provided by Annenberg CPD to advance excellent teaching.
Studying the orbit of Mars around the Sun, Johannes Kepler discovered its path could be explained only if the planet traveled along an ellipse. It was the first of Kepler's 3 laws.
I'm sure you remember that Tycho Brahe had his own system of the universe. In the Tychonic system, the Earth was stationary at the center, the Sun went around the Earth, and all of the other planets went around the Sun. Of course, Tycho believed passionately in his own system, and on his deathbed, he begged Johannes Kepler to use the new observations to prove the correctness of the Tychonic system. It was a touching moment. I have no idea of what Kepler thought of that moment, but the idea of doing what Tycho had asked him to do never even crossed his mind. Kepler was a Copernican to his very core, and as soon as he got his hands on Tycho's data, the first thing that he set out to do was to analyze the orbit of Mars. It proved to be enormously difficult, and no matter what he did, he couldn't make the orbit of Mars fit a circle. The disagreement between the angular position of Mars in the sky and the best circular orbit was 8 minutes of arc. In other words, if he had tried to do the same thing before Tycho's observations, it would have been possible. But with the new data, it could no longer be made to work. And so Kepler was faced with a direct conflict between the ancient Platonic dictum that all motions in the heavens had to be circular motions and the new Tychonic observations. Faced with that conflict, he made his choice. He chose the observations, and he started to search for a different smooth curve that would describe the orbit of Mars. After years of agonizing work, he hit upon the answer. It was a curve that had been known for thousands of years, and it's called an ellipse.
In the most graphic terms, a piece of string and 2 pins illustrate the simple elegance of an ellipse. Since the string doesn't stretch into a different length, the total distance from one pin to the pencil to the other pin is constant. A single point is called the focus. 2 points, the foci. The length of the semi-major axis is A. The semi-minor axis has the length B. The region bounded by the ellipse has area pi AB. The distance from the center to either focus is some fraction of A, EA. The symbol E represents the amount of eccentricity. As in the social context of the word, eccentricity means somewhat off-center. So when E shrinks to 0, when there's no eccentricity, the result is a perfectly rounded figure, an ellipse called a circle. But when E increases, the ellipse becomes increasingly eccentric and increasingly flat. Focus is the Latin word for fireplace. It was first used for the ellipse by a man who became known as the wandering mathematician. His name was Johannes Kepler. And in the sun he saw the greatest fireplace in the universe. In his emotional life, however, particularly as a child, he saw very little in the way of warmth. Kepler's father, a low-ranked soldier of fortune, deserted the family early. His mother was later tried for witchcraft, although it's not known whether Kepler Sr. fled because she had the makings of a real witch. In his father's absence, Johannes was constantly visited by poverty, and despite his mother's alleged charms, by illness as well. His background challenges many contemporary notions about heredity and environment. Though he displayed the skill and curiosity of mathematical genius, Johannes Kepler seemed an unlikely candidate to solve some fundamental problems of the universe. Early in his career, Kepler taught schoolboys in Graz, on the Mur River in southeastern Austria. Like many before and since, he found teaching more frustrating than rewarding. He struggled with geometrical models of planetary motion, but soon realized his astronomical data were not reliable enough. At the dawn of the new century, January 1st, 1600, Kepler set off in search of the most accurate astronomical data on Earth and the man who possessed them, Tycho Brahe. Born into the let-them-eat-cake class of society, Tycho surprised Danish nobility with his decision to do something worthwhile. His penchant for astronomy became his reason for living, and for the last 38 years of his life, he charted the heavens with extraordinary precision. No one on Earth appreciated the potential value of Tycho's heavenly observations better than Johannes Kepler. To him, the data were essential, the key to unlock the door to the universe and to reveal what he called the secrets of the skies. But much to Kepler's dismay, Tycho knew how to keep a secret. So Kepler struggled without Tycho's precious data for almost 2 years. Then, on October 24th, 1601, fate stepped in. Tycho's dying words were, "Let me not seem to have lived in vain." The Danes' family withheld the data, but Kepler managed to make Tycho's last wish come true. Advancing science more than ethics, he stole the material. The otherwise mild-mannered little mathematician was finally ready, in his own words, to wage my war on Mars. Mars, the red planet. Mars, an early Roman god of agriculture and of war. Mars, through the ages, powerful and mysterious. Within the ancient world's concept of the Earth-centered universe, the planets moved in epicycles, and sometimes, as with Mars, the epicycles were very erratic. To account for such erratic behavior, Tycho conceived his own universe, the Tychonic solar system. Like Ptolemy, he placed the Earth at the center with the sun revolving around it. But like Copernicus, Tycho had the other planets orbiting the sun. While Tycho's system fit the appearances more simply than Ptolemy's, Kepler passionately embraced the views of Nicholas Copernicus. This was not only an unpopular view, Galileo would be tried in Rome for sharing it. It was an extremely difficult one to justify scientifically. Consider the Copernican solar system and the problems it presented Johannes Kepler. From Copernicus's revolutionary viewpoint, Kepler had to make mathematical observations from a planet that, rather than being central and stationary, was in motion with all the other planets. Imagine the difficulty of trying to compute the orbit of Mars from a moving platform. A platform that spins on its axis in a non-circular orbit with constantly varying velocity and with an unknown center. This was Kepler's dilemma, and he approached it with a poetic faith in a logical universe. Do we ask what profit the little bird hopes for in singing? Kepler asked. Surely this question expressed his view of the purpose for which he had been created, to discover the secret of the skies. Just as some creatures seem to have been created to sing, Kepler seems to have been created to calculate. And his calculations, which totaled over 900 pages, were enormously difficult. His war on Mars was a patient siege in which many of his weapons were imperfect and faulty. But he employed them with a striking brilliance. For example, to find the location of his moving platform, Kepler used observations of Mars as it returned, Mars year after Mars year, to the same point in its orbit. Then he reversed them to find the orbit of the Earth. By finding a circle, even though it wasn't quite centered on the sun, Kepler had taken a step in the right direction. So now, once again, he attacked the problem of Mars. Still unable to find its exact path, he did manage to find something suggestive in its irregular speed. Mars moved faster when it was closer to the sun, and slower when it was farther away. This would become Kepler's second law, but he still hadn't found his first law. Approximately every 2 years, the Sun, the Earth, and Mars are in opposition. In other words, seen from either the Earth or the Sun, the position of Mars is the same. With another observation, 1 Mars year later, Kepler could triangulate a precise point on the orbit of Mars. Could a circular orbit, even one offset from the Sun, fit all of the points? Almost, but not quite. That is, not within the unparalleled precision of Tycho Brahe's observations. What curve, then, would describe the orbit? The answer to that question revealed the secret of the heavens. With the Sun at one focus, an oval orbit, a slightly distorted circle was called for. And that type of orbit was an ellipse. The ellipse, known to the ancient Greeks and finally rediscovered in the heavens by Johannes Kepler, can be viewed time and time again right here on Earth. It's simply a matter of looking at things in the right perspective. Any circle, viewed obliquely, appears as an ellipse. The Greeks knew the parabola and the hyperbola, as well as the ellipse. By slicing a cone with a plane, they generated curves called conic sections. If the cutting plane is perpendicular to the axis, it cuts out a circle. When the plane is tilted, the circle becomes an ellipse. Tilting it enough for the plane to be parallel to a side of the cone produces a parabola. Tilted farther, the conic section becomes a hyperbola. The ancient Greeks were remarkably skilled in geometric games. By 200 BC, Apollonius earned the title of the Great Geometer for describing such remarkable curves in 8 long volumes. Yet even his pen had barely scratched the surface of the conic sections. In 300 AD, Pappus of Alexandria found another way to describe these curves.
A moving point traces out a conic section if its distance from some fixed point, the focus, has a constant ratio with its distance from some fixed line, the directrix. The ratio of the distances is the eccentricity, E. For the ellipse, this ratio is smaller than 1 and shows how far this focus is off-center. If the two distances are equal, the result is a parabola, a conic section with eccentricity equal to 1. If the point is closer to the directrix, the result is a hyperbola with eccentricity greater than 1.
All 3 conic sections share a common property, and all 3 can be described by a common algebraic equation, an equation that is useful for studying planetary motion. This is the basic formula for describing all the conic sections: the ellipse, the parabola, and the hyperbola. While the ancient Greeks were the first to study conic sections, they never dreamed these curves would influence the shape of things to come. For example, look at the parabola. From the dazzling glare of automobile headlights to the very limited edition 10-meter Caltech telescope, over 1 billion parabolas have entered the marketplace of modern society. Today, among many other things, parabolas are the paths of projectiles, and the heat wave of the future, solar furnaces. Of course, Johannes Kepler never imagined that the hyperbola and the parabola could be found in the heavens. In fact, his use of the ellipse for the orbit of Mars was possible only because it was the only planetary orbit eccentric enough, about 9%, to be noticeably non-circular. Had Kepler waged war on any other planet, he probably would have died believing that circles reigned supreme throughout the universe. But of the battles he had an opportunity to choose, he chose well. And with Tycho's data, He was victorious in the knowledge that the ellipse, as perfect a fit as could be measured, was the mathematical secret of God's creation. These secrets were revealed, perhaps even paraded as the spoils of the war with Mars, as Kepler's 3 laws. Kepler's first law states that each planet moves in an ellipse with the Sun at one focus. While waging war on Mars, Kepler found his second law. A line from the Sun to a planet sweeps out equal areas in equal times. Kepler's second law permitted astoundingly accurate computations of distance and velocity. His third law came 10 years later. It states that the square of the period of a planet is proportional to the cube of the length of the semi-major axis, and it reveals a connection between the motions of different planets. But in 1619, the year Kepler published his third law, he found himself in the midst of the 30 Years' War, a conflict that hit much closer to home than the planet Mars. As Kepler's patrons turned from astronomy to killing religious enemies, he fled from city to city trying to collect old debts. Yet even in these worst of times, perhaps because they were so bad, several patrons paid Kepler to cast their astrological charts. Kepler himself was neither very religious nor political, but with a large family to support, he was astute enough to use astrology to a certain advantage, his own. His predictions were a combination of common sense, good fortune, and, when things looked bleak for the paying nobility, a bit of poetic vagueness. In his book, Harmony of the World, Kepler wrote, "With such fullness of agreement between my 17 years' labor on the observations of Brahe and this present study of mine, I at first believed that I was dreaming." His perception that the ellipse is etched deeply into the grand design of the universe was greater than any noble future he foretold in the service of royalty. A wanderer plagued by fate and circumstance from the start, Johannes Kepler finally unlocked the mystery of planetary motion.
There are 5 perfect regular solids that come to us from antiquity. These are solids whose plane faces are all identical. They are the cube, the tetrahedron, the dodecahedron, the icosahedron, and the octahedron. Kepler realized that if he took a sphere, put inside of that a cube, a sphere inside of that, a tetrahedron inside of that, and so on, that the 6 spheres that he got in that way had the same ratio of radii as the ratios of the orbits of the 6 planets. Kepler was absolutely convinced that he had discovered the secret of the structure of the universe. I have here the book in which he published that great discovery. This book was published in Tübingen in 1596. It's called On the Admirable Proportions of the Heavenly Orbs and so on. And in this book, there is a diagram showing his geometrical model. And here it is. Incidentally, there's something interesting about this diagram itself. This diagram has a date on it down here, which is 1597, a year later than the publication of the book. What must have happened is that the diagram, the plate, was not ready when the book was published, and so it had to be sent out a year later to be glued into copies of the book. Looking back on that incident, we tend to think that Kepler's picture of a sky full of cubes and tetrahedrons and so on is quaint and rather foolish. But I would like just for a moment to take it absolutely seriously and see what it was really about. First of all, in a period when almost no one else believed in Copernicus, this model is solidly Copernican. It makes no sense whatsoever without the sun at the center. The second thing you have to remember is that it's only much later, in the time of Newton, that we start to imagine a universe held together by invisible forces. Before Kepler, the universe was a planum. That means it was filled with crystal spheres. What Kepler was doing was replacing the crystal spheres with these perfect geometric solids. And so you see, Kepler's idea was both daring and yet solidly in the scientific tradition of his time. The third point is that it was very successful. His picture explained the ratios of the orbits of all of the known planets. And furthermore, it gave him a reason why there had to be 6 and exactly 6 planets, because there were 5 and exactly 5 regular solids. And finally, the model served to motivate Kepler. In all the enormous work that he did throughout the rest of his life, the work that led to the discovery of his 3 great laws, all of that work was done to justify this picture, which he always had at the back of his mind. Now, his idea is wrong, but it's wrong for a perfectly legitimate scientific reason. For example, it says that there must be 6 and only 6 planets. And we now know that there are more than that. There are at least 9 planets, and maybe even more. And so it's wrong. It makes a prediction, and the prediction is not correct. And we must discard it. It's not a viable theory of the universe. But it's not something for us to laugh at either. The value of a scientific idea lies not in whether it ultimately turns out to be right or wrong. Instead, it lies in whether the idea is fruitful, whether it leads us to new ideas, whether it leads us to progress. And by that standard, Kepler's silly model, which did indeed to turn out ultimately to be wrong, nevertheless, by any reasonable standard, must be regarded as one of the most important, legitimate, scientific ideas in all of history. I'll see you next time.
Although Kepler's geometric model was incorrect, it led him to discover 3 laws that describe the heavens with precision. Each planet orbits the sun along an elliptical path with the sun at one focus. A line from the sun to a planet sweeps out equal areas in equal times. The square of the period of a planet's orbit is proportional to the cube of its semi-major axis. These are Kepler's 3 laws.
Funding for this program is provided by Annenberg CPB to advance excellent teaching. For information about this and other Annenberg CPB programs, call 1-800-LEARNER and visit us at www.learner.com.